A little bit of background on what we do. So we are developers of Nextflow. Nextflow's been around almost coming up to 10 years now in terms of its development. The kind of came out of CRG, where we were based before, which is the Center for Genomic Regulation. My kind of background came from like biological backgrounds, and then did sort of bioinformatics as a PhD. I actually spent 6 months or so at EBI in Sanger before, and really looking at it in the RFAM team, which is a really nice experience for myself prior to starting the PhD. And then created and sort of started working with Nextflow with Paolo Tommaso, who's also, and our whole kind of concept is around making these pipelines easier to use, so making them, developing them in a way, and in developing Nextflow outside the context specifically of just the pipelines, but also the kind of whole wider things, so the data management side of it, and running that stuff in the cloud as well. So let's start with a little bit of kind of background on what we're trying to solve here. If you're familiar with bioinformatics, you'll know that you often are in situations where you're trying to write complex pipelines. This is an example of an ancient DNA analysis. And each one of those steps there, each one of those points is essentially a piece of software which has to be written. And then you have to kind of link these things together. And obviously the kind of linking of these things together and running them in different environments is the real challenge that we're trying to solve here. So this is actually an NF core pipeline for ancient DNA analysis. These kind of little roadmaps are pretty cool to write. What we're trying to do here is basically just visualize what's taking place in this. And then you want to kind of run this not just once, but for every sample that you have. And there'll be points where you need to pull these things together, break them apart, and then kind of run them at scale on any environment. And that's the kind of the key thing that we're trying to do. Okay, so how does it kind of look like? So what's the main challenge here? Well, we all are dealing with more and more data. So we have larger data sets. And the kind of thing about the bioinformatics pipelines in particular, we can run them in what we call embarrassing parallelization. So this is a way where each sample that you have essentially gets placed onto it as a job, and each of those samples kind of runs through your pipeline. And this kind of means that we can have hundreds or tens of thousands or sometimes even millions of tasks which are run in this kind of distributed way. And it's a little bit different from other kind of analysis that you'll see. So you often see things like, what's the comparison with something like Airflow or something like this. And in those situations, they are typically dealing with code that they're writing themselves. So you're writing something from scratch. And then you're also doing things like, a SQL query, or you're doing some kind of transformation. In terms of bioinformatics, we're usually using lots of tools. So we're taking stuff off the shelf. So we are taking things from something you'll download from GitHub, or maybe it's a script that you have taken from the postdoc in the lab. Maybe you're in a situation where you're taking something from Conda, and you need to basically pull all of that stuff together into a pipeline, into a run, and then kind of run it at scale. So this creates a massive kind of challenge in terms of building up all of those different tools, building up those different dependencies, and then kind of running them in a way which can be reproducible and obviously kind of fair with all the kind of elements of that as well. So here's an example. This one was actually written at the Sanger, to be honest. This is actually called the companion parasite genome annotation pipeline. It was a very early Nextflow pipeline that kind of got us excited. That was developed by someone. And each one of those circles here is a piece of software, essentially a tool. And you can see the links between those things. There's what we call the arrows here, what we call channels, is really linking the dependencies, essentially saying from this process goes to that process, goes to that process, all the way through here. And you can see here that this one is made up of 70 different processes. There's about 55 external scripts there, and installing this thing and kind of putting it in a way where you could not just develop it for the first time, but then share it with someone or publish it, provided a massive challenge. And this is something that we did very early on with Nextflow, is actually use this example and try to see, okay, how could you even do this before? Like, how can you install all those different pieces of software and then kind of do that on different environments? So if we look at other examples here about taking a typical publication, this case here that we're trying to look at, how could you take a typical bioinformatics paper and reproduce it? What is it required? Even when you've got all of the pieces, even if you've got all of the code, all of the kind of thing to set up. And say this example was, say, about 280 hours to try and replicate the paper. It kind of shows the challenge which we're dealing with here, even with everything defined and we can have all the versions, etc. It's still a massive challenge to do this in a way. It's kind of worse than that though, in a way. So even if you have all of that stuff, you can still be in a situation where the same application, or essentially the same pipeline, when it's deployed in different environments, can have different results. And this is something that we published as part of the Nextflow paper back in 2017. And we showed that across multiple different pipelines, when you look at, for example, genome annotation, this is using the companion pipeline I showed you before, on that situation, you ended up with basically different genes being expressed or called differently depending on which environment you installed the pipeline in. So basically, we showed that pipeline installed on Mac and on Linux, and we ended up in a situation where the genes that were called differentially expressed were different. Also, the same thing with like the start and the stop codons for those genes in those different environments. And basically, we were able to show that you really need to containerize your stuff to be able to control everything and to kind of say, okay, this is my reproducible result. The reason this comes about, well, these pipelines are super complex. You've got all these different steps, and the software which has been installed on all of that has all the dependencies, and you can end up in situations of just rounding differences or how the underlying code is analyzed, even in situations where you can have the same effect. And this results in like different results in terms of our science, which is not something we want to be dealing with, particularly when we're trying to make the science reproducible and applicable to different places. So our kind of goal in terms of this is there's obviously FAIR, which a lot of people have heard of before, so making it findable, accessible, interoperable, and reusable. I've kind of added onto this in my own definition of this, which I think is sort of expanding what's really required in the modern age. So obviously making the things findable and your code findable. This means your pipelines. We're obviously big believers in Git and Nextflow, and we'll see a lot of that over the next couple of days. Making it accessible, not just usable by informaticians or people who can use the command line, but making your code, your pipelines that you develop, usable within other systems. So maybe accessible via API, or being able to create a very easy user interface for experimentalists, for example. Interoperable is obviously key, that when you write your pipeline once, you don't want to have to rewrite it for every cluster that you want to run on or every cloud that you want to use. You really want to make these things accessible and then interoperable in that place. Reusable, obviously reproducibility is a big part of that. I showed you just before about how critical that is. And then kind of equitable in terms of free of bias, scalable. We want to develop on our laptop and then scale out to the cloud or cluster as we need, as well as test it. And what I mean by this is more around using best practices in terms of software development. So having unit testing around modules and making sure that the pipelines that we develop are able to be kind of tested and using these kind of best practices as well. So all of that leads us to the Nextflow itself. And what is Nextflow? Well, it's a couple of things. One of it is a language, so it's a way to write pipelines. You can think of it as a syntax in this way, or a DSL, so domain-specific language. In Nextflow, you can take any code. So if you've got existing R, Bash, Python, command line stuff that you have, you basically take those, what we call like blocks, those processes, and you link them together with Dataflow programming. And then you define the dependencies with containers, and then wrap all of that inside of a Git repository. And once you have the definition of your pipeline as a Git repository, then you can run it on any of the different platforms here. So we support all the major cloud providers, as well as things like Slurm and LSF, Grid Engine, Kubernetes, and all of these kind of execution. And there's a kind of key thing, it's a couple of key things, I guess. One is like the separation between these two things. So the definition of the pipeline is completely separate from where the pipeline runs and the configuration of this. And this has been a big part of Nextflow's growth, has been this clear distinction between those two things. It means that the whole world can come together and write a single pipeline on the same code base in GitHub, independent of where it runs, independent if they're running on their laptop, independent if they're running in AWS or in Google or Azure. It's absolutely the exact same code, not a single kind of thing changes in that regard. And then the other thing is that the technology is changing a lot. So things like AWS Batch were not around 5 years ago. And now we're in a situation that you can basically write that pipeline without worrying about necessarily what's going to happen in the future. There's going to be new execution platforms which are going to be coming out. There's going to be new hardware. There's going to be all sorts of kind of things that we're going to need to run on. We don't want to have to rewrite our applications every time that we want to do that. And there's examples of this, like pharma companies who are running pipelines which are validated say FTA validate, and they can't change anything. And all the stuff becomes really important as you want to scale it out as well. So that distinction has also led to this community side of things. So where Nextflow really has been able to develop a community of people developing those pipelines, coming together and having best practices and around that as well. Okay, so what's different about Nextflow and kind of how does it work, and how does it separate itself from other things? So the first thing is that to say about Nextflow is it's a DSL, so domain specific language. This means it's a programming language written on top of another programming language. That underlying language is Groovy, which means you can use that as well as Java underneath. So if you're familiar with Java and comfortable in typing that, you can kind of access all of that stuff underneath. Insane. So being a DSL, it's designed for the task at hand, and that task is writing pipelines. And there's typically not so much that's required. You don't need to know Groovy or anything to write Nextflow pipelines. And being honest, I know very little, next to none myself, in terms of running the pipelines. It's not so much required. The importance of that, though, is that it's not like a specification here. And the fact that you can access that if you need to, so in corner cases or in situations where you need to kind of go around what's possible in Nextflow, you have this underlying programming language as well, which makes it really important, makes it very flexible for that, but also very quick for prototyping and developing the pipelines out, and also readable, which is key as well. It uses this reactive programming model. This is where the flow comes from in Nextflow, so Dataflow. And this is a model which is essentially taking each of your kind of inputs and running them through the pipeline like a push model from the top. It's best seen in some examples. We're going to see some of this and how that looks like, but it's really like pushing those files kind of through the pipeline itself, as opposed to something like make, which is kind of pulling them through from defining your outputs. This is very scalable. This is very powerful. It takes a little bit to start thinking in this way, but once you grok it, it's very strong in terms of its ability to scale up. So we can have a single pipeline which can have millions of tasks. From that, even on a very kind of small CPU, you can kind of drive the execution of that orchestration. As I say, once you start get the hang of this thing, it's very very powerful as well. We have this concept of being kind of self-contained, or each task. So each task can be thought of as a unit of compute. So each task might be like run star align on the sample, for example. In that case, that this idea that each kind of task is kind of its own isolated unit of compute, it really led itself to being used in situations like AWS Batch, but also like submitting a task to a cluster. And it also linked in very nicely with the idea of containers. So, the first versions of Nextflow didn't have containerization. It was kind of before Docker came out. But the approach was just absolutely perfect in terms of the way it kind of encapsulated this idea of sending each task as something which would be submitted to it. And things like AWS Batch, which came out 2017, kind of idealized that as well, where each single task would be run on that environment in an isolated way. All the dependencies are kind of independent of the others. So it means that you can submit this out, and it means that you can have like compute across multiple different execution environments as well. And finally, there's the separation of the kind of execution, so it's the definition of the pipeline from where you run it. And this is kind of leads to the portability. So these are kind of four key parts which make up Nextflow from a kind of philosophical perspective. And we're going to go through each of those and see what it looks like in practice now. So let's take an example of bioinformatics. Let's say we want to run a single task here. So this is BWMM, and I'm running this with my reference and my sample. So this is something that you might run in the command line. Maybe you've got a Perl script or a Python script, which is going to call this. And typically in Nextflow, you don't want to rewrite this. So you've got the script, it works for you. I don't want to have to go through and kind of change that. In Nextflow, we kind of decorate, so we kind of define the process itself. So we basically have the same section here, the exact same script. And what we're going to define is the inputs. In this case, this has a process, which is called align sample. It has an input, which is a reference, and an input, which is the sample. And then it has an output, which is what we're trying to capture from this, which is the sample.bam file. And then we have the script section. And you can see that script section is exactly the same as what we had before. So once we have these two parts now, so the key is kind of linking these things together. So this is a definition of an Nextflow process for a line sample. how do I use the output of this process, essentially the sample.bam, in the next downstream process? Well, this is what we do with channels. And you can see here that the output of this process becomes the input of the next process. And this is the kind of key to how Nextflow links these things together. And you get this kind of parallelization, which is driven from this inherent connection via channels. And channels are the kind of the key thing here, linking this together. So here's the align sample, here's the index sample here, and you can see that just by using that as an input. In practice, what this means is that you can think of it like the align sample process and the index sample process are alive. They're kind of sitting there waiting. The way that the Dataflow programming model works is that each of those processes is just waiting for its input. So index sample is sitting there saying, okay, I'm waiting, what's going to happen, what's going to happen. And as soon as that sample BAM enters that channel, it's essentially emitted from that channel, the index sample process will start. And this thing kind of happens, cascades through the whole pipeline. So this is why it's a reactive programming model, because all the processes are sitting there waiting for their inputs. As soon as their inputs are received, in the first case here, like the reference is received and the sample is received, fires off, execution begins, and that kind of cascades all the way through the rest of the pipeline. In terms of the syntax, it's designed here trying to be, for bioinformaticians and for scientists as engineers. It's not necessarily you have to rewrite your existing applications. So on the left-hand side here, you see another process. This is the quantification using Salmon. You can see you define some inputs, some outputs, and then on the right-hand side, a workflow section, essentially linking these things together. We're going to spend more time over this over the next few days to get kind of familiar with that. In terms of the Dataflow programming kind of concept here, it's a little bit of a definition of what it looks like, but you can think of that you have your input data. Each one of those input data becomes essentially an element in a channel, then goes through the different processes in a parallelized way. You then have operations which can be performed on those. We have on the kind of strict definition of what those things are that link it. These are the channels. These are what we call the Dataflow variable here. They are asynchronous first in, first out queues. And that kind of means that sort of what happens is the linking between two processes is driven by these channels. And this is the kind of the thing which fires off the execution of the next one. And it creates this, or I guess like automatic parallelization. You don't have to say, okay, for my files in my folder, do X, Y, Z. By simply saying, this is the input, this is like basically creating a channel, we call it, with the files. Each of those files becomes an input of that channel, becomes an element in that channel, which kind of flows through the rest of the pipeline. So how does it look? So imagine that I had 3 files, so Z, Y, X here. And by creating a channel here, which contains those 3 things, we have the kind of definition of the channel saying 3 elements, the process, which is the kind of definition of what's going to be running in that process. And then for each iteration of a process or each kind of run of a process, we call it a task. And then each of those tasks is then going to output something. So a lot of words, but a lot of kind of like language here to try and say that there's this definition of a channel, which essentially holds the data and links processes together, the process, and then each iteration of a process is a task in itself here. If we want to kind of write this one, imagine that we created a process for FastQC, very kind of simple process here. It's just a 2-line in Bash where we're making FastQC files, and then we're doing a FastQC on that. If we started this pipeline and we said, okay, the input here, which is my sample channels, so this say channel from path, was a single file, in this case, sample.fastq. This process would run once. So we would say Nextflow run, FastQC would run once. If I then change that though, and I said, okay, my sample channel now contains all of the files in that directory, so anything which match.fastq. The FastQC process would run for as many times there was files. So each file would be an element in that channel. FastQC is sitting there waiting, this is the process, and it would be running on each iteration, basically on each element which had been fired off from that channel would create a task of FastQC. And this is how that kind of parallelization kicks off and runs in that regard. Here's another kind of visualization of that where each file becomes an element in that channel, kicking off FastQC. Okay, couple of comparisons here. Often people want to sort of compare Nextflow with other kind of commonly used ways of running pipelines. So one thing that's different about Nextflow is that it combines both the language and the runtime. This is not like a specification, as I said before. So it means that any changes we can put in very fast, we can iterate very quickly. In terms of the development of Nextflow, it means that those two things are tightly tied together. And in terms of like kind of industry standards here, I think it's very important to point out that those things can happen in this way. If you're in a situation with developing something like CWL, you have to be sure that let's say the person who's developing the runner, in that case, is going to work on all these different platforms. And what we try and say in this regard is that Nextflow has the ability to run on all the different platforms. In this sense, it ends up being can be used in a much sort of wider range of environments, as opposed to relying on a different runner for each situation that you want to launch the pipeline. So this makes it quite different in the sense it's a DSL, so it's written on top of this programming language. We can access that underlying programming language for situations, kind of dependent on the definition of the pipeline itself. It tries to be very concise in the sense that you can understand, you can look at Nextflow code and read it and make it kind of readable. And it's really kind of community driven here in terms of its stuff. So Nextflow is open source, Apache 2.0, it's kind of very active community, pushing changes into that, and something which makes it quite widely adopted in that regard. Nextflow is much more similar to Snakemake, so CWL. So again, kind of command line tools. The key kind of differences around it is Nextflow's got this push model, this Dataflow model, which is much more kind of scalable in terms of compared to Make, where you have to kind of pull things through. Nextflow is a little bit more flexible in terms of its data structures. So we're not having to define the file outputs that you're trying to find. And so you can kind of link in there. And then it has support as well for all the kind of major container runtimes. So we have Docker, Singularity, but also a whole bunch of other ones which are available as well. And I think the key thing here is the ability to link in with all the clusters in the cloud integrations. So whether that means pulling data from S3 and then pushing it into and running on Azure, or linking in with your LSF, Nextflow's integration here is super powerful. Very kind of, very Git-centric, as I said before, but like very kind of really linked into the idea of using source code management as kind of part of it. And obviously it's built on Groovy and JVM. So that was a rough kind of overview of what's taking place in terms of the Nextflow syntax. Once you've got your pipeline though, how can you run it? And what's the kind of different deployment scenarios here? And we said before that once you've developed the pipeline once, you don't need to change it for these different ways of running the pipeline. And it's very important, particularly around like development of the pipeline or sharing them or making them available to other people, that you have this flexibility inherently in Nextflow itself. So if we look at the local execution, this is what we're going to be doing. Like most of the time, it's what you're doing when you're developing the pipeline. You're just using Nextflow run and you're running on a single virtual machine. Often you'll see this with kind of running on your laptop, but also things like testing. If you're running like a GitHub action to test the pipeline. And here you're operating directly on that operating system with or without containers, typically with containers in this case. So like each Nextflow task becomes a Docker run command that runs on that single kind of operating system on your machine. And it uses like a local storage for the intermediate files for running that. Nextflow is obviously the kind of main usage for it in terms of going out is in a what we call centralized cluster orchestration mode. Here, Nextflow submits each task to cluster. So it becomes like a Slurm job or an LSF job. And Nextflow will take the requirements for that job, memory, CPU, queue, whatever, and take those and convert them into that task. So basically it's able to interact with the cluster in that way. And typically here we're using a shared file system as well for the intermediate files, which makes it kind of very quick in terms of the kind of starting up of this. And this is kind of a really kind of powerful way to launch and very quick in terms of its execution between this as well. I think Nextflow supports something like 10 different schedulers when operating in this mode. What's become very popular, particularly in the last couple of years, is cloud managed services, and particularly cloud managed services with batch. So there's now AWS batch, Google Life Sciences, Azure batch, and more coming out all the time. Nextflow is basically kind of like a cluster in the cloud, and Nextflow submits each of the tasks to the batch API, which in turn will place that task or job in a queue, and that will spin up a virtual machine for that task, either in a one-to-one ratio. So Google Life Sciences will take the requirement for that single task, spin up a virtual machine based on those requirements. AWS Batch and Azure Batch will spin up different virtual machines, and you can put multiple tasks onto each of those jobs when they run. From a user perspective, though, you're just saying Nextflow run with Batch, and then it's going to basically do the scheduling for you, and it's going to place those jobs on those virtual machines. If there's no virtual machines there, they'll spin up. The task will run. When your pipeline's complete, they'll spin down. The nice thing about this is that bioinformatics workloads are very lumpy. So you just have a ton of sequencing data you need to analyze, or in one situation, you just need to kind of go through that whole access GPUs, or maybe you need to use like FPGAs, and like that's not stuff that people have got lying around typically, and you just want to use it when you need it. So that kind of makes that really nice in terms of the ability to kind of spin those resources up when you require them, and spin them down when they're not required as well. Here you're typically using something like S3 for the intermediate files as well, and Nextflow has this integration with all of the different bucket storage there, which is kind of a key point as well. If you want to future-proof yourself, and some of our users are kind of going in this direction where they want to control exactly how that horizontal scaling works, and this is the kind of cloud-native Kubernetes-like execution. Here, every single task itself becomes a pod which runs on Kubernetes, and those pods in itself get placed on these virtual machines, which are then kind of spun up, spun down, based on the requirements there. And this is something that's kind of more for teams that can or have the ability to manage that infrastructure, but something which is very powerful as well. And obviously a lot of interest in this area. What does it really look like? Well, if I have a Nextflow script, a Nextflow pipeline, and I say Nextflow run, it's going to run onside my machine there. So just basically imagine I'm just running on my desktop. If I then went to add what's called the Nextflow configuration, if I was going to add this configuration in here, an executor, I want to run on Slim, I want to use this queue, and I want to use for each task 8 gigs of memory and 4 CPUs, point it with the container that I want to use, then it's going to run that. So Nextflow will submit each task to Slim. The key point is like the abstractions here, and then like kind of the abstractions that are built in. If I want to take that same pipeline, so when I've run this locally, now I've run it on Slim, and I want to go run it in the cloud, I simply can switch out here the executor that I'm using here, point it at AWS Batch. And Nextflow has the same abstraction for memory, for CPU, for container. And all of that stuff can stay the same, and the pipeline can be essentially the same as well. AWS Batch hasn't got a concept of queue in this regard. So you can switch those things out, and then you have this ability to take those pipelines and run them anywhere. And again, this is something which stays in the config, not in the definition of the pipeline itself. So that the underlying code can remain the same there as well. Decoupling these things, so decoupling the definition of the workflow from the configuration is the real key thing to making these pipelines portable and to be able to run in these different environments itself. So containerization, containerization is key to the portability as well. And it was kind of a kind of thing early on, which we developed. So containers at the time, so this is 2014 or so, they were used primarily for web services, for kind of long-running jobs where you would want to develop some service, you would put up in the cloud, and you would have that container to have all the dependencies defined, and then you can use it like that. Well, we kind of reimagined them at the time in a way that you could apply them to data pipelines. And if we think that we have a pipeline, I showed you at the very beginning, each of those single tasks is kind of submitted out, and each of those tasks is running in a distributed way. Each of those tasks can become a container job. Essentially, each of those tasks just becomes a Docker run. And this is kind of what's led to things like AWS Batch and the like, because they are literally just container running jobs for that. If we compare them to what existed before, there was virtual machines prior to containers, but containers were much smaller, much faster in terms of the startup, so you can bring them up very quickly. They're lightweight in terms of their size and the ability to spin them up very quickly and define them. There's also like this whole kind of the tooling around it, like the Docker tooling became very popular and very easy to use in our applications. So we're going to go through the session later on, but how we can build those containers, can use that tooling to to make it kind of simple. And they're also composable, which means you've got layers on them. So you can build from one container on top of another container, on top of another container. And those layers themselves and the kind of tooling to create them can be done in an automated way. And this kind of all together kind of helps us in terms of our definition of the dependencies for our pipeline. And we can have multiple containers inside the same workflow. We can build them very quickly. We can integrate our own custom scripts in there or custom requirements, dependencies for those workflows as well, using that as well. So Nextflow had support for Docker very early on, back in March 2014. There's also now support for Singularity. That's something which is typically used when you're running in a shared environment. If you don't have the ability to use Docker, because sometimes Docker requires elevated privileges, things like Podman as well is available. And I think there's a couple of other containerization engines that are supported by Nextflow. Key point though, each job, each task becomes a container job and then is run on the infrastructure itself. So when to use containers, I hope the one thing you can get out of this workshop is just always use containers. Once you get over the kind of initial understanding of what's going on, it's just so invaluable in terms of the use. And it's something which has been growing massively in the last few years. But when you start to find new dependencies like this, you just thank yourself so much in the future. When you have to go back and run something from 6 months ago, or you have to share that with someone else, and instantly there's just not this kind of dependency hell of installing all of the stuff that you previously had. So something that hopefully you can take out of this workshop is to use the containers. In terms of Nextflow itself, so it's kind of growing quite rapidly. We have about 12,000 developers who read documentation every month. A big part of that has been not just like contribution to Nextflow open source, like the runtime, the language, but also actually the pipelines. And this has been the kind of most incredible thing to watch is kind of Nextflow's adoption in things like NF Core and the way that people have come together to develop those pipelines, same code base, and then having the ability to kind of use those in terms of production, pulling them out, and there's kind of been driving a lot of Nextflow's use as well. There is a whole bunch of things you can have. There's obviously syntax highlighters if you use things like Visual Studio Code or other ways they want to edit that thing. You can highlight that things up. In terms of our adoption of Nextflow, I mean, mostly focused at the moment still in bioinformatics areas, really kind of in places where there's a bunch of sequencing taking place. I would say the majority of applications for Nextflow are still in the sequencing space. There's a bunch of imaging, machine learning as well, where it's used. There's nothing inherent in Nextflow that kind of linking it to bioinformatics or all this. There's really very little in there which is specific about bioinformatics, but I guess because of where we're coming from and because of like the adoption is really in that space. In saying so, we're starting to see it being used in wider applications, image analysis of like satellite images or in geology and other areas as well. I think we've seen some stuff in like astrophysics and anywhere there's kind of batch computation is where Nextflow really works. In bioinformatics, it's really kind of, we have a lot of different pipelines that are made up of multiple different steps. Kind of that whole kind of containerization aspect of it is a key part of it as well, which drives that as well. NF Core is a big part of that. NF Core is this collection of community pipelines that have been developed over the last few years. This is a fantastic place to go take stuff off the shelf and run. There are things like the RNA-seq pipeline, but also a whole bunch of like 50, I think it's 50 or 60 of these pipelines available now. And they're really kind of a great starting point in terms of being able to take stuff off the shelf, get running quickly, and kind of in production pipelines as well. The RNA-seq pipeline is something like 70 different steps. And you really get kind of a full analysis available to you at your fingertips, off the shelf as well. So that's kind of a high-level view of Nextflow. The language itself, the way of running the pipelines in different execution environments, it provides a very nice way to use containers, and it's kind of sort of language agnostic in terms of what you can do with it and taking your existing code without kind of rewriting that from scratch as well. We also have sort of an element around that. So as we've developed Nextflow, it also became kind of clear that there was a whole bunch of challenges associated with running pipelines that are just not the running the pipeline part, but all of the kind of data management, making it available to a whole bunch of people and doing that as well.